You can see some of the other recorded sessions from previous sessions. But yeah, definitely with the YouTube channel link, I would give that just a few days before that's fully active. But Discord, you guys should actually, I encourage you to hop into that as soon as possible if you haven't already. And if you're a teacher too, if you could hop in, there's a teacher space. If you could just say hello or something, just so I know who the teachers are, so I can separate you from the students, and I can give you guys certain permissions that maybe your students don't fully have. I think that's about it for that slide.
Great, Cody, thank you very much. So yeah, what we'd like to do is let's actually recap. It's a while since we've actually really chatted about what is this challenge about. By the way, this is a fairly open session. So if you have any questions or whatever, if you want to interrupt us, please feel free to do so. We would like this entire program to be as collaborative as possible. So yeah, what is this challenge about? Well, we have two things already. From Blueshift, we have the opportunity to fly our payloads on the inaugural test flight of the first bio-derived fueled rocket to go to space. So that's what we have from Blueshift Aerospace. From MaxIQ, we have modular electronics kits from which we can build our space-worthy payloads. So that is what we have. So what is actually the challenge? The challenge is to create a unique and insightful experiment based on the UN Sustainable Development Goals using the sensors provided. And you will, as you will see as we go through today's session, that you're also going to be able to customize your own, develop your own sensors within reason that will connect to the kit. The students will be able to develop methods to test payloads and collect preliminary data to compare to the Blueshift flight. So the thing is, because this is an inaugural flight, we don't actually have actual data, empirical data of the flight, the flight profile, the vibration profile, etc. It's all there in theory, and the engineers have put it together. They've been doing bench tests, they've been doing other kinds of rocket engine tests. But when we actually do the flight, what we're going to need to do is actually collect the data. So this is a wonderful opportunity for the students to actually develop a methodology to collect that data of that flight profile, and then actually be able to contribute that data to the development of the entire program. The desired outcome is to answer the question, how would you use this opportunity to test your satellite payload with the intention of developing it further into an orbital picosatellite? So this flight, this suborbital flight, is one flight on the way on the journey for Blueshift Aerospace to actually to get to orbit. And so what we're doing is that we are making a number of payloads available, payload spaces available. I mentioned it a little bit further down, 3 payload spaces available to actually launch your picosatellite into orbit. So that is actually the reward for the challenge. And so your required output would be a presentation of the project and results during World Space Week, which is always every year is 4th to 11th of October. Sorry about that typo there at the end. My shift must have been a little bit stuck there. So yes, what is the reward? The 3 top judged presentations will earn their teams an orbital launch of a payload into orbit with the first Blueshift flight. So what I'd like to do is I'd like to pause there because what I'd like us to do is maybe have a little bit of a discussion around that, about what actually is this challenge. So do we have any questions in that regard?
No questions from me.
Okay, great. I can see that we do have Seth Seth is here from Blue Shift Aerospace. So this is actually also your opportunity to ask Seth any questions that you may have. I know during the onboarding sessions and the information sessions, we did have a number of questions for Blue Shift. So please, if you actually do, please feel free to ask those questions. Okay, great. What I'm going to do is let me then continue. And let's actually get to, so what is it that we've, how are we going to start? So yeah, thank you very much, Daniel, for putting together, Daniel and Cody for putting these together. And one can certainly learn a lot more about the various sustainable development goals by clicking on the image and on the link. We are going to be sharing these slides afterwards. And we did find certainly that during through the projects that we've been conducting alongside this particular challenge, we do have students who are focusing on a number of these goals, like for example, life on land, very much looking at, one can only observe from space if there is really widespread soil erosion, flooding, forest fires in very isolated areas, crop failure, etc. Life below water, a lot of the time that is all about algae blooms and understanding how algae actually absorbs carbon dioxide in our oceans, etc. So there's a number of great opportunities where one can support these sustainable development goals in order to develop your payload. I'd just like to add is that what we are doing is these kits, we have nicknamed them the Sdg Kits, the Sustainable Development Goal Kits, because we've been running programs with the United Nations Development Program, as well as UNICEF have now come on board in terms of supporting what we are doing and how we're rolling out. So what I'd like to do is let's take you through what you have already. So what I did is that I checked on all of the shipping today, and I think that from what I can gather, the only person who hasn't received their kit is actually receiving 2 kits, and that is Linky Lee from Pennsylvania State University. So her kits are actually still on the way, unfortunately. But everybody else has received at least one of the kits. So what that has in it is it has the weather sensor, which will give you temperature, air temperature, as well as relative humidity, a light sensor, which gives you visible light, natural light intensity measured in lux, as well as UV index, a soil moisture sensor. One can be quite creative how you want to use that. Anyway, on a flight, but you could certainly use it in the environment surrounding the rocket launch. Your processor, you have a power unit, which is also a USB programming interface, which you are definitely going to be using. You have your display and your Blue Shift mechanical chip with the QR code on the back to take you to our page. And then 8 of those little connector chips, these little connector chips. So what I'd like to do now is I'd actually like to, Bianca, can I actually hand over to you so that you can take us through how we are going to be deploying these particular chips, as well as how this links with the hardware that's been developed.
Judy, actually, before we go into that,
Daniel,
why don't I just give a quick overview for our K-12 friends that are here as well, just before we get into the nitty-gritty of some of those details, going a little bit too granular. So real quick, what I want to do actually is I want to go back to a previous slide. I'll just do a quick screen share. One of the questions that actually James Tyson asked in the chat is one of the things that we will address, and we'll kind of go into the hardware portion of that, and Bjarke will work through that. But if you guys take a look at the actual kits that you have, so I've gone ahead and created one as well. So the image that you have there with Cody showing his actual sensor, everything comes preloaded in this STEM starter kit. So one of the things that's really nice is that there's different tierings that have kind of naturally been created so that we can support all of our grade bands from K to 12. The 3 p.m. session for the undergrad and graduate levels will kind of go in a little bit deeper and further as to what the different opportunities are. But for a lot of the things that I'm going to talk about will be kind of revolving around the 9 to 12 band, right? So for a lot of our K to 8 educators, specific questions as to how you might be able to decompress things or make things a little bit easier and engageable for the younger grades. I think the teacher space would be a great place to be able to ask those questions. But with that being said, the next 12-week block that we have kind of set aside is going to be exploring using specifically the STEM starter kit. All right, so a lot of the work that you guys will be doing will be based off of the things that we explore here. For the 9 to 12 grade bands, right, a lot of you guys might be more interested in being able to collect and create sensors for yourselves, right, and how those things are going to be integrated. So that's kind of what Bjarke is going to talk about in just a minute. But what I want to make sure is that everyone, at least at this point, has gone through the process of powering on and taking the time to actually set up their STEM starter kits. So for me in particular, one of the things that I'll share with you guys is that I have my Kibana dashboard set up. So when you go ahead and follow the links and go through the videos, you'll be able to actually set up your own dashboard as well. But here, this is something that I've been running for the past 24 hours. So one of the things that you can see is kind of the STEM starter kit, being able to see when the sun is setting, right, and during the night. And then here it also caught the sunrise in the morning. So now our ambient light values out by the window is how I have that set up. So there's a lot of different things that you can kind of do along the way. So in that kind of pathway, one of the things that we've broken up is how we will follow that. And then that chunking will kind of make sense in terms of timing for our K to 12 participants within the context of a school year and what that might look like. All right, so I just wanted to take a minute to make sure that we were all kind of on the same page with moving forward before Bjarke kind of goes into a little bit more of the granular aspects of the program.
Great. Thank you very much. And yeah, what I did is I collected my kit from the other side of the room. And so, yeah, on the back of this Blue Shift chip is this QR code, which takes you to the page that we are constantly updating with all the links to the videos, all the materials, getting started guides, absolutely everything that you need. And so yes, what I'd like to do is, Bjarke, can we please hand over to you to take us through what we're going to be, how we're going to be using our processor in preparation for our flight and also in preparation for receiving our flight hardware.
Okay. So what Daniel was holding up was a starter kits, which consists of a little computer core here. So I'm just gonna go a little bit slowly through this thing here, but probably not so slow so anybody who is familiar with it is getting bored over it. And also just remember, this is a long course where you're gonna get through this a number of times. But this is the computer core. This is the central piece that you have today. There's a little MCU on the back here. It runs Wi-Fi and Bluetooth. There's 7 buttons here on the front, cat touch button. There's a couple of LEDs. And this is your central communication device. So when Daniel before showed you the data he had on the dashboard, excuse me, then it was uploaded via the Wi-Fi here. There's also a little screen. So there's a little screen here you get along, and that screen will show you as much data as possible. It's a graphic screen that have 128 by 64 bits. So obviously it's not the most ideal thing to watch a 4K movie on, but for the data you get here, it will do. And then there's a number of sensors. So the sensor that you are having in your kit is that you have a weather sensor where there's a little cloud and a sun down here. So there's a weather sensor like that. And then you have a light sensor that looks like this thing here. There's a little light bulb. And the last thing you have is that you have a interface. And I'm trying to find the same kind of interface you have. I'm kind of like just gonna hold this one up because it's gonna look like very much like this thing here. There should be a little USB icon on it. So yeah, Judy have one there that looks more correctly. I think this thing here is actually closer, but still not the same. But that's this device here powers your circuits. It also allows you to reprogram your core if you want to, so you can program it in Arduino and Python and things like that. So if you want to do that, then you use this thing here to program it. And it also gives you communication over the serial port, so you can see what's happening inside here. So all the data that's getting uploaded over Wi-Fi is also coming down the serial port. So if you, for example, want to treat the data locally on your computer instead, or write your own local computer program, and then the data comes down in a JSON format, so you can simply just capture that and treat it the way you want to treat it. But what I'm going to focus on, and this stuff here just mentioned here, is what Daniel and Cody and Judy is going to go deeper into. But I want to kind of like talk about what's coming later on in the program. So there's other sensor coming. So there's one with a rocket on here, which is an accelerometer. There's also a couple of other sensors that we are still kind of like prototyping. Some of them are coming with the kit, and some you can opt to buy if you want to kind of like focus on that. One of them is environmental air quality sensor. There's a little fire down here because it's a CO2 kind of sensor. There's also a GPS, which have an option for a battery on the back here, so you can kind of like save the almanac a little bit better. But the thing that you're getting with the kit here, with your dealer here, is that you're getting a new core. So this core here, which is green, so unlike the white ones, is a little bit different because it have the same CPU, MCU here as the other core have. So you can see this is the other one from the back. So that looks like that on the front. But what this also have is that it have a camera interface here. So it can take one of these small HDMI cameras. Not HDMI, 1080p camera. So it's very small. As you can see here, I don't know if it ever get better, but that's, you plug that in here. Then there's an SD card here, which allow you to store data. And then there's an expansion port here. And the expansion port, so that's what you get here. So if you want to use the camera, it's extra, and SD card you have to buy and things like that. But you're getting this thing here in your kits. Now, you can then choose that you want to do different kind of experiments. So if you want to, for example, fly it on a balloon, sorry, I have a green screen, so therefore the colors is kind of like going away when we have a green thing here behind you. But if you want to use this thing here to a couple of other experiments, there's an option for a LoRa radio that you simply plug into the expansion port here. Obviously, if you want to do that, then you need two of these things here so you can communicate from the one to the other. And some of the project you can do then is you can fly it on a weather balloon, and you can use the LoRa radio to communicate data from your balloon. We call it flight station to a ground station, which is the same as this one here. So the ground station have a LoRa radio, and it uploads the data using the Wi-Fi. And the flight station is this one here, just with a LoRa, and all the sensors you had before is just connected to them. So the sensors is just similar to to what you had before, just connects to this core here, so you can simply just stack them here on top. You get it right, so like that, and you can keep on connecting your different cores here on the top, and of course you can connect them in between. What you're also getting with this kit here is an ability to expand your play with making your own sensors. And there's two options. The one is a very simple one, which is a little PCB like that, very tiny little PCB, but it allows you to solder in, like, for example, a light sensor, LDR, light dependent resistor, and then you have resistors you put it in here to do like a voltage divider for your sensor. But obviously you can use any kind of resistor-based sensor that you pick up. And this is for a through hole. So you have a solder station, you just solder them in and this thing here. And the code on this thing here is prepared for this. So whatever you put in here, it will take the voltage and report it on JSON file. So you will see it. You don't have to modify the code. So if you just want to do a little bit yourself and say, I want to actually do my own sensor just because, it's a learning opportunity, then you can do it with that. There's also another one. It's going to be white in the final version. And that's a little breakout board. Don't know if it's clear, it's probably not. But on this breakout board here, you can see, you can connect I2C sensors. So like all the other sensors that normally on the board is I2C. But if you have like something you buy from Adafruit or Microelectronica or SparkFun or one of those guys that have breakout boards, then there's standard 0.1 inch holes here. And there's I2C, there's SPI, and there's 2 IO pins, and there's 3.3 volt and ground, of course. So you can kind of like put that in. But if you do that, you need to then make your own code. And for that, we are providing a framework where once you kind of like want to fly with this thing here, it will download the data from this sensor. Obviously, the framework doesn't include all the other sensors in the code, but then you can add that because the software that we pre-install, it's also open source, and you can then take that, modify it or learn from it and make your own code. On a later stage, much later stage, you will also get a mobile battery solution here. So this is a LiPo battery. So you have a LiPo battery here. It have a USB-C connector here, so you can charge with, and you can also power your circuits stationary with this thing here without the battery inserted. You can just power it like that. You cannot program using this USB-C. Then you still need this device. Sorry, but you can power it. And this is kind of like if you want to do a balloon flight and things like that. Obviously, you need a battery backup. What we are including with the kit is a AA battery module that just takes normal AA batteries. Judy, I don't know if you have one there you can hold up because I don't. But it's simply just a white chip that's kind of like this length here, kind of like 2 chip long. Oh, Judy have one there, that's great. So, and that takes the standard AA batteries. And that will be interesting, for example, if you want to fly it on a model rocket. So you can fly it on a model rocket, then you don't have to have a power bank or something like that with it. And it can fly and it can store data on the SD cards. And then you can kind of like look at the flight profile that way and see if your sensors work or anything like that. The way that once it goes into to the Blue Shift rocket is that each institution have a layer that's similar size to a flat piece of a CubeSat, so 10 by 10 centimeter, around 4 by 4 inches. So that will be what Judy holds up there. So that will be this board here plus 6 sensors. So 3 by 2 sensors out. And that's what Judy holds up. That's 10 by 10 centimeter. Actually, It's 96 by 96 millimeters, so there's a little bit space around. And what happens is that this module here then uses CAN to communicate to the mother station. So there's these ones here have a headroom of 1 centimeter. So in a 3U satellite, a 3U CubeSat satellite, there is 30 of these. One of them, or more than one, probably is going to be the kind of like the mother station that then communicates to ground station via Bluetooth radio, and also provides power via Bluetooth radio. And then it goes into what I call a spine. So this is like 30 centimeter 3U long, and it have these connectors. Actually have it all the way down, but for the prototype here, there was no reason to solder all those in. And this thing here then goes in to the spine here, and in each layer there is a similar one, and there's a spine on the other side that kind of like hold this whole thing together. And then you have your 6 chips going out here to the sides, and this this setup here then communicates with CAN to the bottom here. So you don't have to have power or other communication, so you don't need LoRa or anything like that. The software that's preloaded will communicate to this thing here with the CAN, so CAN bus, and then the power will be distributed. You will have around 250, maybe 300 milliamp of power for your project, which is, should be sufficient for what you're doing, since you're not running Wi-Fi or anything else. So the components on that board here, maybe it takes up 70 milliamp. All our sensors is like sub 1 milliamp sensors. So there's plenty if you want to run something else. So that's how it lowers into the rocket. Blueshift is we haven't cleared with Blueshift exactly how our communication protocol is, but that's not a concern for you because you communicate to a mother board that with a CAN, which is already done, and then we arrange with Blueshift how we communicate with them and do a downlink with them. The data you get on the SD card, there's an SD card on board. So of course, when you fly in a rocket or whatever you do with it until then, all the data is stored there in with all the calculations and things like that on a card. The data that gets downloaded either with LoRa or with CAN is being downloaded with a very compressed data form. It's called message pack. So it's being downloaded with that, and that allows us to kind of like maximize the bandwidth of both the LoRa radio or whatever we use on the Blueshift satellite. We also intend to use the same technology for the project we sent up to the International Space Station, where we have done it before. The earlier projects has only been storing data to the SD card, but we want to do in the future is also communicate with a downlink and again communicate with the motherboard with CAN, and we will then figure out how we have an interface to the International Space Station's communication interface. Daniel, have I missed anything?
I think on the technical side, I think that pretty much covers it. What I'll do is I'll take back we'll open it up to questions first, and then I'll take back over, and then I'll kind of give a little bit more context specifically for our younger students and our K-12 educators as to, so how do we take the STEM starter kit and integrate that into what it is that you just talked about, and why is it that we should care? So why don't we start with questions first?
How do you put your unit on a model rocket to take data?
So, yeah, so I don't know, Cody or Daniel, if you want to pitch in, but otherwise I can. No callers, that's fine. So the dimension of this is 32. It's 32 millimeter wide, so it should fit in to a number of SD rockets. And the way we're going to do it is we're going to make it so you can make like a long string of chips, so you can actually lower that into the rockets. So anything that's 32 millimeter in diameter, maybe slightly more. I think that the ones we looked at from SDs are like 34 millimeter inside. So, you know, we can lower that in, and then you will just have it longer. So we will make an interface so you can have the stuff in the rocket. Then the data is getting stored on an SD card. In a rocket launch, model rocket launch is typical, 5 seconds up and 30 seconds down. So there's a lot of data happening in that window. So it's too cumbersome to try to make sure that we can download the data using LoRa or something like that, because there's much more data you want to collect. So you get it on a SD card, and then you can take the SD card and you can open it as a comma separated file and into an Excel spreadsheet. And then you can see, your data. It's basically your accelerometer that gives maybe an idea about the flight profile and things like that. So the other thing is that what we're going to do is that we're going to do some Stl files, 3D printed files that allows for these to be secured in a variable. So it's going to be a parametric file that allows you to say what is your diameter, inside diameter of a rocket, and it will make some holders that you can click that into. You obviously have to print those 3D holders there, or you can have another cardboard solution if you want to do that, to put it into the rocket. But obviously there have to be a little bit of space for whatever sensors you want to include on that. And that's the reason why the AA battery is also included, is for the model rocket, because that gives you enough power for that. We use the AA battery, by the way, even on balloon flights. We used it on 2-3 hours balloon flight without any problem. So it will be useful there. It will be useful in a model rocket. And the battery is also just 32 millimeter. There's a little bit, of course, thicker, and that's the reason why the accurate 32 millimeter diameter is probably not enough. It's probably more like 34 millimeter inside diameter.
Okay, good. Thank you.
You're welcome.
Excellent, Ruthann. Thank you very much for that. Bianca, Ruthann is from Virginia, and they were participants on the ThinSat program. So that's going to be quite exciting for the students. Bianca, we do have a question from Roy. Roy is from Taylor University. Roy, I was just wondering if you would like to answer that question directly, please.
Ask.
You want to ask?
Yeah, go ahead. Hello.
Hello.
My name is Roy Lokenville at Taylor University. This is Rob Cartwright. He's also assisting with our satellite club. So he's going to ask the question.
Yeah, I was just trying to make sure that LORA is what you were talking about, and then I see a confirmation there in the comments, so that's good.
Yes.
And I know that would just be for if you're doing wireless, because yes, you could do the SD card. I see that comment as well.
Yeah, so the LoRa here, so the radio here is 433 megahertz. So in the US, you need an amateur radio license to use that. We have earlier used 915, which of course is license free for you guys, or 868 in Europe, but we have the best result with these ones here. We have flown and had radio communication from a balloon to a ground station with over 200 miles in distance. So you get the LoRa. One of the reasons why we use LoRa is because it have a link budget of 168 dB. So it's the sensitivity minus 148 dB makes it ideal for this kind of stuff here. It doesn't spend a lot of energy transmitting. It's 20 dB, and then you maybe have a couple of dB gain on the antenna side. But the sensitivity is the thing that makes it great. And because of the spectrum, it's kind of like a noise independent. And you probably know LoRa since you asked about it. So I don't know need to oversell it to you, but there's actually satellites right now. There's something that called tinygs.com, where you can go in and see a lot of satellites flying with LoRa. and you can actually build your own ground station. And we're going to experiment that because the TinyGS network is actually using this MCU and it's using this radio. And so we're just going to try to make an experiment with that, because I think there's a learning experience in actually downlinking data from existing satellites that flies with LoRa. So that might also be an option. Thanks, Roy.
Thank you.
Now, up in the when we're up in ELEO space, what satellite system do you guys use?
When we fly in space?
Yes.
Yeah, so we have only done payloads so far. We haven't done radio communication in space. So we delivered payload and MCU on the ThinSat program, and the ThinSat program used you should be familiar with it because the guys down the road from you has actually done the global star radio that was used there.
Right.
So when we do so look at our solution, not as something that necessarily is flight ready. I mean, there shouldn't be anything that stops you from trying out this thing here. We have launched it in rockets, obviously, in order to be on ThinSat. And by the way, when I launched in ThinSat, they were put together with the same connectors as these ones. There was just like a one screw in each corner here to kind of like hold it tight. But you can actually fly this thing here. We also flown it like this thing here, both on Antares and SpaceX to the ISS. Yep. Of course, in vacuum when it's just cargo, and it worked brilliantly up there. So we kind of like, according to our guy who do our paperwork, Mike Miller, he says we are readiness level, TIL level 9, I think it is. So we have around 45 satellites that have been flying with these things here in the ThinSat program, and of course, couple in the ISS. So yes, if we were flying in space, and what we want to do when we want to fly this in space, so the idea is that we follow Blue Shift. Blue Shift is doing a suborbital launch the first number of times. By the time they're ready to go into orbit, then we should also be ready to actually try this out. And at that point, we're going to use LoRa. We're following the footstep of the guys in TinyGS. The reason why LoRa isn't so well used in the space industry is because of AMSAT's kind of like holding on to use good old hand radio protocols, 2 meter and 7 centimeter and that kind of stuff that has been used a long time, and the protocols that have been used there. I think they've been very open towards going into using LoRa. And of course, there's a lot of other radios like S-band, X-band, all those radios, but that's kind of like as a little bit over the top for what we want to do. We want to kind of like all our technology is kind of like low bandwidth. So you can do, I think it's 137 kilobit per second or something like that with LoRa. So it's going to be a picture here and there. We download not necessarily HD movies or anything like that. On the other hand, can we also piggyback on like a LoRa network where you can, because in some of the network solutions out there, you can actually go in and subscribe to a network and say, please, can you download this thing here for me? You actually take over the ground station for like the 10 minutes of flyover. So we kind of like hope we can do that also. But when we get there, Roy, it's going to be LoRa.
Great. Bjarke, thank you very, very much. What I'd like to do is I'd like to introduce Sasha Derry to everybody from Blue Shift Aerospace. He is their CEO, inventor, leader, champion.
Rocket engineer.
Yeah, he's the rocket scientist. That's it. He's the one we all aspire to be. And so, Sasha, yeah, please. We would like you, please, to introduce yourself. And I have to say, I I watched a video, a documentary that was put together on Sasha and Blue Shift Aerospace by Forbes. Very, very inspiring stuff. And very much, Sasha, your passion is environmentally friendly applications and how green can we go. So it really links very well with our challenge, which is all around how can we, the challenge is to develop payloads that will assist with reaching some of our sustainable development goals. So Sasha, please, I'd like to hand over to you so that you can introduce yourself.
Sure, thank you.
And
Thank
take
you
it
very
from
much.
here, please.
Sure, thank you very much. Can everybody hear me okay?
Yes.
Yes.
Wonderful, okay. Thank you, Judy, very kind. And I want to give credit to also where credit's due. The real rocket scientists is our engineering and tech team. They do all the magic. I come up with some ideas and they come up with 1,000 more and make it actually happen. So by the way, if you guys didn't see it last night, our full biofuel powered, non-toxic fuel, nearly carbon neutral fueled rocket engine, hybrid rocket engine was successfully ignited last night. Thank you, Seth. He actually put in the chat. Oh, that's the Forbes article. Maybe you can pop in the chat. We had a successful engine test, full-size engine test. This is the engine we will be using to take max IQ payloads up into space, beyond 100 kilometers, and in fact, ultimately to 6 to 8 minutes of zero G time. And we are the very first company to have ever launched commercially using a bio-derived fuel, let alone a bio-derived fuel that you could literally eat, not that you would want to, but you could literally eat, and it is very close to carbon neutral. So we're very proud of what we're doing here. We've made a little, I live in a town of, our business is at the former Naval Air Station in the town of Brunswick, in the state of Maine in the United States. And we made a little ruckus last night at about 8:35 p.m. With igniting those engines. So we are very excited. You know, what we're fundamentally about is curiosity and exploration. And I think that lines very strongly with what not only what Max IQ is doing, but to the students, the professors, the researchers who are incorporating the Max IQ technology into what you're doing. So we are extraordinarily excited to and pleased that we've signed the launch contract with Max IQ for taking up to 60 student and research payloads to space on an annual basis. And our goal, our very lofty goal, is to get our launch underway before the end of the year. That is 2022. We have done this before, and we're about to do it again. It took us years to develop our engine that launched Stardust just a year ago. But once we had developed our engine, it took us, it took us a number of years. It took us like 4 or 5 years to develop the fuel, the proprietary fuel. It took us a year and a half to develop the engine. And it took us nine months to build the whole rocket, find a place to launch, work with the FAA and launch it. So we are on a similar time frame. We're already working with the FAA, and we are very close to determining where we're going to be launching from here, likely at the state of Maine. And we have some backup locations outside the state. And we are extremely enthusiastic and excited about sparking passion, interest in STEM, in exploration, and general science and research in space. So really, really excited. And I recognize a couple of faces here already on this chat room. So I'm also more than happy to answer questions about what we're doing and the parameters around our rocket, Starless Rogue.
Wonderful, Sasha. Thank you so much. So I think that I'm not sure if you were able to be with us when we discussed the challenge. But the thing is that what we've really stressed is that this is the inaugural launch of in terms of a suborbital flight. And so what it is it's actually it's a test flight for all of us. So the thing is that what we are really encouraging the student groups to do is to use their accelerometer and actually collect the data so that we can start simulating that that launch profile. Because the thing is that that is always going to be so critical when developing a CubeSat payload for when we actually go to orbit. We really, a lot of that test process is actually using that launch profile to make sure that it'll survive to being deployed. So yeah, I think that we're going to be getting some, I'm very confident we're going to be getting some really, really useful data for your team. And so please don't buy any expensive sensors. You know, just tell us what you want, and you know the
That's
thing is that we can all make it happen.
Very cool.
Bianca and Co have developed, maybe Bianca, I'm not sure if you actually just want to, if you want to lift it up as well, is an interface board so that a number of the student groups can actually have their own sensor. They can actually attach a sensor of their own choice. So that, there we go. You know, so the thing is that that's why I'm saying anything that your team wants, let's actually put it out there, because it's definitely going to be aligned with what one of the groups wants to research as part of their challenge. So
awesome.
yeah,
So accelerometer is going to be really, really informational for us. One of the big goals we got from folks, the researchers that we interviewed 2 years ago, was they wanted to make sure that we were not accelerating too fast, not pinning their experiments to the wall. So we're actually limiting, and actually makes our rocket a little bit bigger, but we're purposely limiting our G forces to 5G directional. Now vibrational. So the whole idea is to limit to just, you know, around 5G. But, you know, another good, really useful data points will be the vibrational data and the different axes. So that is wonderful information, and it'll be very, very helpful to know, and especially to know in the payload bay itself. So that's really exciting. I know Judy, you've mentioned that to me before, and I apologize. I did have to join late today. I apologize.
No, that's absolutely great. Yeah, so certainly that is going to be useful for those groups who feel that they would like to do some experiments with the carbon dioxide and volatile organic compound sensor. We will be able to provide that to them on special request. So yeah, we could definitely have a look at some experiments in the payload bay regarding, you know, what is happening in terms of the combustion reaction. Are we getting any gases coming through? What is happening in the environment surrounding the launch site, etc. I can see that the team from Taylor University has a hand up. So please go ahead.
So when you're talking about the payload bay, are we talking about the rocket during launch or ISS, or where?
For us, it's the payload bay in the rocket during launch. Yeah, suborbitally.
We wouldn't be powered up, would we? Our past experience is we're never powered up there.
We will be happy to provide you power.
Okay.
Yeah.
That'd be new.
Yes.
Yeah, I think let me just fill you in on that. So what this particular project is a suborbital launch, and we're going to be recovering the payloads. And so the whole idea of it is that we have power. Bianca is making sure that all our units are powered up through the entire flight, up and up, weightless and down again. And the data that you collect will firstly be saved on the SD card that you have in your interface. And secondly, we're going to be having a downlink. So we're going to have redundancy in terms of being able to recover our data.
Okay, so if I'm understanding, if I'm understanding, then that's the conversation, Sasha, where you talked about the 5 to 6 seconds of weightlessness. And okay, this is all new to me. I hadn't seen any launch trajectory charts or anything yet, so I didn't know how this works. Okay.
Sure. Yeah. And the initial flight will be going over just 100 kilometers. And then from there on out, our plans are to go to 350, 400 kilometers and get to that 6 to 8 minutes of zero G time.
Okay, cool.
Absolutely. Are there any other questions for Sasha? I'm very aware of the time because it is during our school days. So, or are there any other questions for the team?
Okay, so if there's no more questions, I just want to be conscious of the time, especially for our K to 12 participants. Just to recap, right, for our university and colleges, like I stated at the beginning of the meeting, at 3 p.m. you guys will have another session where you will be able to ask a little bit more of the technical questions, and Bjarke hopefully will get to go a little bit deeper. But what I do want to make sure that we get to is just so that we can end at 10:30, and then if people are available to stay longer, they can feel free to do so. But why is it that K to 12 schools care, right? So a lot of that technical information that Bjarke just shared, believe it or not, the actual satellite in terms of the firmware, right, and the core sensors that are flying all will remain the same. So what that means is any libraries that we are using for the ESP32 will remain the same from what you guys are using on the actual Sdg STEM starter kits, right? So that practice is what we're really going to be focusing on for the next 12 weeks. And if you'll be with us for the 6-week extension for the next 18 weeks as well. So a lot of the sensors will end up becoming redeployed in that way as well. The USB interface that you guys have in these STEM starter kits as they begin arriving, or if they've already arrived, allow you to be able to interface with different programs. So the big one that we'll be using in the 12-week sessions that are to come after this meeting are going to be through Arduino. So a lot of the information now at this point has already been populated. For specific links, you should be able to access those things through the Discord. So you'll see a lot of that information be posted there. There are also going to be instructor notes that are posted for teachers. All right, so really this is geared more so for K to 12. And the instruction notes, the way that they are written, will be geared for more high school students. And the activities that follow will be in the outline for high school, but obviously they can be scaffolded down for younger grades as well. With this being said, the libraries that you guys use, right, one of the things that you guys will have an opportunity to do is actually be able to integrate them into what actually flies onto the final satellite itself. And in the future to come, Bjarke will give an outline for how that will occur, whether it will be a full bin compile or if it'll be a separate method of having that occur is still kind of to be determined. But you'll have those opportunities. Specifically with the testing portion, one of the things that each school will have the opportunity to be able to do is interface through using that core. So in terms of how you're going to test your custom sensors, Arduino will be the process for how you guys go through that. And then the nice thing is, in terms of the software, the libraries will transfer one-to-one. So that was one of the things that Bjarke wanted to make sure was available to all of us in terms of making all of our lives simpler as we kind of go through this testing phase. So with the STEM starter kit by itself, a lot of the work that we'll be doing will be looking at this kind of breakdown of where it is that information is moving, right? So how is it that the sensors are collecting that data, how that data is then being communicated to the actual processor, and then eventually how is it that we see that data come live into Kibana and the dashboard. So I just want to go through the rest of these slides real quick, right? So I started getting into where we kind of go from here, right? So for the K to 12 schools, we'll outline this in a 12-week outline. And then for the 6-week edition, it'll be a add-on of going through communication and operations for a 4th and 5th iteration. So if you think about it in terms of 3-week blocks, the first 3-week block that we'll be exploring will be using communication as a breakdown to be able to kind of integrate this idea of how it is that these satellites work. So the STEM starter kit uses a couple of different protocols. The first two that we'll be exploring will be I2C and SPI. So that will be in week 2. But in week 1, when we think about the science, one of the things that we'll kind of explore is this idea of analog signals versus digital ones. All right. So If these are things that you guys find useful, right, obviously those are sessions that will be available and they'll be kind of tailored in a way for student participation moving forward. But also you could think about it as, for those of us who are teachers, right, how you are going to take that information and then be able to kind of scaffold down. All handouts and teacher notes and slides will be available to you guys after each session. The instructor notes should be available starting today, and I do believe that Judy will be sending out an email for that in particular. All right, so everything in terms of this slideshow is also available to you guys directly. I put the link in the chat, and then I'll also be posting the link again into the Discord so you guys have it. The Discord will be our primary methods of communicating in terms of things that students are struggling with or things that you are struggling with as an educator in terms of getting your students to understand. Any questions from the instructor notes and things like that, I'll be able to address quickest through the Discord as well. So please use that as kind of your primary source of getting information and the main hub for us to be able to communicate through. All right. So in terms of why it is that we care as K-12 with the STEM starter kits, hopefully we're starting to understand, right, the integration into the actual satellites that will fly. It fundamentally runs the same thing as the actual starter kits as well. All right. So that's just the last thing that I want to make sure that we kind of get to. Do you have anything further, Judy?
Daniel, I'm good. I'm very good.
Okay.
Let's see if we have any questions.
So at this point, it is 10:29, so I wanted to make sure that any K-12 teachers that need to get going are able to do so. This meeting is being recorded. All meetings being recorded will be available as well, and I think Judy will take care of where those recording meetings will actually exist. But if there's any information in terms of questions for what we've covered so far, I will stay on for a couple of minutes, I believe, right, Judy, Yarka?
Correct.
So if not,
That's fantastic. Daniel, we just had a question in the chat, maybe to just attach the Discord invite link if you have that at your fingertips. Yeah, I think also from my side is that what we've done is between Daniel, Cody, and myself, we've put together a program that we really feel would be valuable to everybody. However, we are extremely open. We are completely, totally open to suggestions of topics we should include. After all, this is actually your program. And so we want to make absolutely sure that we cover everything that you would like to have covered. We have a large network of experts, industry experts, who are very eager to come in and assist with different topics as they would be. On Sasha's exit, he actually mentioned that he would be very happy to put together an entire webinar with his engineering team as well to tackle a lot of the questions. So please make those suggestions. I would recommend probably on the Discord that you do make those recommendations so that we can actually start scheduling workshops according to your needs, not only in terms of what we think you would like. Emmanuel is asking the question, is it possible to include coding for space engineering and stuff like that? Yeah. And Emmanuel, absolutely. Won't you please just make that suggestion in the Discord channel as well, so we can follow up on that. Emmanuel, this is his third mission that he's doing with us. He's participated in the ISS mission last year and one before that as well. Great. Any other questions from anybody? Yes, please, from Taylor University. Yeah.
So you have the Discord. Do you have another place where all of us up and down can communicate? You know, that's like we can easily post pictures. I've used Slack a lot. I haven't used Discord before, so I assume Discord allows us to put pictures, and we can because we're more than willing to be an open resource to the undergraduate kind of people, but we also found in past satellites that we wind up needing to ask a lot of questions. And so.
Yeah, Discord runs just like Slack. It's just able to integrate the younger crowd as well. That's all.
Great.
Great. Wonderful. Anyone else? Or otherwise, what I'd like to do is actually close the session. Thank you very much, everybody. Daniel, really, thank you very, very, very much. You've been doing 99% of the heavy lifting on all of this. And so, yeah, the same time next week, and same time next week, we're going to be going into the science of the communication protocols that we're using. So we're going to have our science session starting next week. Great. Daniel, let me hand over to you to close.
Yeah, I was just going to say in the chat, I was just going to post out that the link for next week's session should be available in the coming days. Judy, I believe, will be sending out an email, and then we'll also be posting that link to the Discord. All right. So next week at 9:30, we'll start, like Judy said, with session 1, and then we'll look at the science of kind of how it is that the communication protocols take over and what they actually communicate. Right. So that should be exciting stuff.
Thanks all. Cheers. Till
Have a good
next
one,
time.
everybody.
Bye.